In this video, we'll be looking at a few new reactions of alcohols. For several of these reactions, we are just getting an introduction, and we will talk about them in a little more depth with other topics later this semester. One of the most important reactions of alcohols would be the oxidation of alcohols. Now, keep in mind from Gen Chem, we focused on oxidation and reduction from the perspective of electrons. So oxidation is the loss of electrons. Well, that is still true in organic chemistry, but we look at it from a different perspective. Oxidation is an increase in the number of carbon-oxygen bonds and or a decrease in the number of carbon-hydrogen bonds. Now let's consider different types of alcohols. If we have a primary alcohol, this can be oxidized to give either an aldehyde or a carboxylic acid, depending on the oxidizing reagent that is used. For a secondary alcohol, this can be oxidized to give a ketone, and a tertiary alcohol will undergo no reaction. So tertiary alcohols cannot be oxidized, but methyl, primary, or secondary alcohols can be oxidized. A traditional oxidizing agent that had been used for many, many years is called chromic acid. This is H2CrO4, but typically, rather than measuring out some chromic acid, one would use potassium dichromate combined with sulfuric acid, which produces the chromic acid in situ. Chromium-based oxidizing agents were quite popular because we have chromium 6 being reduced to chromium 4+, while an alcohol is oxidized. These are not very environmentally friendly, so there's definitely been a move away from chromium reagents, but because we're talking about them on paper, we can stick with the traditional reagents as well as see some new ones. In addition to chromic acid itself, there are a few other chromium-based reagents that had been developed. Here we have pyridinium chlorochromate, or PCC, and this one is pyridinium dichromate, or PDC. In addition to the chromium-based reagents, there's a whole host of other reagents that have been developed. This one in particular is called the Des-Martin periodinane. It was developed by Des and Martin. This type of compound with the iodine in those bonds, this is a periodinane, or it's just called the Des-Martin reagent. Now, why do we have different oxidizing agents? Some of it is about avoiding the environmental toxicity of chromium reagents and developing something that is not as harmful, but in other cases, it's also about selectivity. Now, with a secondary alcohol, for example, whether we use chromic acid or PCC, PDC, Des-Martin periodinane, in each case, this is going to be oxidized to give a ketone. So a secondary alcohol will give a ketone. For a primary alcohol, this is where the reagent makes a big difference, because with a primary alcohol, if we use chromic acid, we would make the carboxylic acid. Always remember to count your carbons. We're starting out with 1, 2, 3 carbons, and we're ending with 1, 2, 3 carbons. So the carbon that used to be connected to the alcohol, this is now the carboxylic acid carbon. On the other hand, if we use PCC or PDC or the Des-Martin reagent, then we can oxidize a primary alcohol to the aldehyde. So different reagents give us different products when it comes to the oxidation of primary alcohols. We will talk more about these reactions when we're looking at the preparation of aldehydes and ketones, as well as the preparation of carboxylic acids.
One very important reaction of alcohols is the preparation of esters. So keep in mind, esters have a C double bond O connected to an O that's connected to some R group. So esters can be prepared starting with a carboxylic acid and reacting it with an alcohol to give the ester with water as a byproduct. Alternatively, you can start out with an acid chloride and treat it with an alcohol to give the ester with HCl as a byproduct. We're going to learn a lot more about these reactions and nucleophilic acyl substitution reactions in general a little bit later this semester. So here is an example where we have, this has the common name of isoamyl alcohol, and this can be esterified with acetic acid in the presence of sulfuric acid to give isoamyl acetate. This compound is responsible for the scent of bananas. The last type of reaction that I wanted to mention has to do with the protection and deprotection of alcohols. So let's say we have a particular starting material that contains a carbonyl and it contains an alcohol. And we want to carry out a Grignard reaction so that the R group shares its electrons with the carbonyl carbon, pushing these electrons up onto the oxygen. But because of the presence of an acidic hydrogen, instead, the Grignard will just act as a base, grab off that proton, and that will quench the Grignard. So one approach that can be used is to convert the alcohol into a different type of functional group, one that is not reactive with a Grignard reagent. So there are a number of silyl ether protecting groups. So these can be made, it's typically a chloride, and you might have a methyl and a T-butyl group. And basically what happens is that the alcohol is going to become bonded to the silicon. So our oxygen is now connected to the silicon, which is connected to the methyl group, and the T-butyl group. So now we have converted our alcohol into an ether. Okay, it's a silyl ether, but it's still an ether. So at this stage, we can add our Grignard reagent, and this will react selectively here. So step 1, we add that. Step 2, H3O plus, and we are going to get, so our R group is now connected, and we still have our silyl protecting group. We were able to do the reaction that we wanted. But what if we wanted this alcohol? Well, we need a way to get it back, because protection is only helpful if we can also deprotect, right? So we want to convert our functional group into something that's not reactive, but we need a way to convert it back again. So silyl ethers are quite common because the silicon forms a really strong bond with fluorine. And so there's a number of different fluoride-based reagents that can be used to deprotect. So a common one is called TBAF, tetrabutyl ammonium fluoride. And you can just think of this as a source of fluoride. And so this is going to form a new bond with the silicon. And we will get back this alcohol, and our R group from our Grignard has added, and then we'll have left over this now connected to a fluorine. So there's a bunch of different silyl protecting groups, There's the TMS ether, which is the trimethylsilyl. There's TES is triethylsilyl. This one, T-butyl dimethyl, is often just called TBS for T-butyl, right? So a lot of different protecting groups, and there's a ton of information known about how you can put on the protecting group, what types of conditions different protecting groups are stable to, and then how you can deprotect the functional group to recover your original functional group. So the advantage of protection deprotection is that this gives you an opportunity to carry out a reaction that you otherwise couldn't do. Another piece of good news is that there are so many protecting groups that have been developed. And for each protecting group, you can find many different ways to put it on and many different ways to take it off. The bad news is there are so many different protecting groups, and each protecting group has so many different ways to put it on and so many different ways to take it off because something didn't work. Somebody had tried all these other protecting groups and couldn't find one that was stable to the conditions that they needed. Or it means somebody picked the right protecting group and they tried 20 different ways to make it, and so instead they had to develop a 21st way to make it. Same thing with deprotection. Another disadvantage to protection deprotection strategies is that it adds at least 2 steps to any synthetic sequence because you need 1 step for the protection and 1 step for the deprotection. And then another disadvantage is that it's rather wasteful. So you have your starting material and you put on this other group, and then at the end you take off this group, which isn't used at all, right? So you're wasting a lot of atoms. So it's not aligned with a green chemistry approach to synthesis. So reaction of alcohols to form esters, that is something that we're going to be looking at later on this semester. As far as protection and deprotection goes, I just wanted you to be aware of that as part of the process of multi-step organic synthesis. For a long time, it was seen as a huge advantage to be able to use all of these protecting groups, but the general philosophy has changed to where a synthesis is viewed as much better, much more effective if it minimizes the use of protecting groups, because that is going to minimize the steps, it's going to minimize the waste, and so kind of a changing mindset in organic synthesis.